Before going into Coulomb's law, let's take a look at Charles Augustin de Coulomb's experiment. In the late 1700s, he used a torsion balance to investigate electrostatic forces. On the right, you're going to see a historical torsion balance, but let's take a look at a clear schematic of what this involves. This picture is pretty old. So, as you can see, there's some sort of gold-colored scale around the circumference of the cylinder to read the separation of charge. There's also an opening at the top of the cylinder for you to insert a charged pith ball. So over here we have a negatively charged pith ball, just as an example. So usually this isn't inserted at the beginning, but there is a hole to allow us to insert this. We'll just keep that in mind and continue up. There's another rod that contains something called a torsion head at the very top that also has a dial that can measure the amount of twisting that occurs in the torsional fiber that hangs down. This torsional fiber comes down and there's two pith balls on a balance, and when you start the experiment, you're going to leave the pith balls alone and calibrate the torsion head so that no twisting is experienced at all. When you're ready to do the experiment, you drop the pith ball, either negatively or positively charged, into the glass cylinder through that hole, and then you observe the amount of twisting that occurs. So it's actually here that Charles de Coulomb was able to derive Coulomb's law. So the amount of twist that the torsion fiber had was proportional to the force of the electrostatic charge. He also found the inverse square law of Coulomb's law. So in a bit more detail, let's say we have two charges. So we have this charge over here, capital Q, in red, which I'll just call the red charge, and the another charge in blue, represented by little q. So with these two charges, they're separated by a distance r, and we're going to assume that these two dots are point charges. And what a point charge is a charge that has a radius that's really close to zero. So essentially think of them as specks, and that they're one singular point. Whether they are attractive or repulsive doesn't really matter at the moment, but we know that there's going to be some force acting on each of these point charges. So if we take a look at this charge here, we know that the blue charge is going to act on the red charge in terms of a force. And the direction of that force is going to be from the blue charge to the red charge. So we have this vector here representing the electrostatic force from little q to big Q. So we write this as F of little q to big Q. Similarly, you have the exact same thing on the other side. Big Q is going to exert an electrostatic force on little q, so the order in which we write it is going to be F with a subscript of big Q, Q, big Q and little q. So continuing on, we have these equations for Coulomb's law, and this corresponds with this, while the blue one corresponds with this force. It says, Coulomb's law basically says that the force, the electrostatic force, is equal to K times the magnitude of each charge multiplied by each other divided by r squared. And there's also a position vector here with the unit vector pointing in the direction of whichever direction the force is acting in. So let me just clarify, we have a force. If we're looking at the red charge over here, we know that little q is exerting a force on big Q, so that is the direction of the position vector. So looking at the other point charge, blue, it's going to experience an equal but opposite force. So we know that just from this diagram, both of the magnitudes can be the same between each other, but they're going to be opposites. So this is Coulomb's law, and now we're just going to take a look at some of the constants and units involved. So in SI units, both of the charges are defined in coulombs, or C. The forces are defined in newtons, just like all the forces we've talked about before in previous classes. K is actually called Coulomb's constant. It's a universal constant, and it can be defined as 1 over 4 pi epsilon naught. So epsilon naught is actually the permittivity of free space, where free space just means vacuum. So whether you use K or use 1 over 4 pi epsilon naught with this value, it doesn't really matter, but you'll find that we have this expression here for a reason. So we have that expression to help us simplify some of the calculations that we do, and we'll see that later on. So another thing that I wanted to talk about is that Coulomb's law is really similar to that of the gravitational force. So instead of having KQQ over r squared for the gravitational force, you have GMM over r squared. So if we were to compare the two and find a ratio, we'd see that the electrostatic force is about 39 orders of magnitude larger than the gravitational forces on this Earth. So that's pretty shocking, and it's also very awesome because it means that the electrical forces are the forces that hold all of us together, every electron and proton in its proper place for everything. Last but not least, let's talk about what happens if we're looking at more than 2 charges. So let's say that there are 3 charges like in this diagram. So we have 2 positive charges and 1 negative charge up here, just as an example. And I've labeled them Q1, Q2, and Q3. Focusing on Q3, we know that Q3 is going to experience a repulsive force with the positive charge. So we know that it's going to experience a force pointing away from it. So that is the force of charge 1 on charge 3, so F13. Then you have a negative charge from Q2, so it's going to pull the positive charge Q3 towards it. So there's an attractive force, and that is the force of 2 on 3. So to find the total or net force acting on Q3, we add these force vectors up, just like we've done in the past with forces, and we get a net electrostatic force. What's very special about this is that the principle of superposition holds. So this allows us to find the net electrostatic force, or basically the combined effect of all the charges on one point charge. Although there is no reason it should work, every experiment that has been performed on this topic has verified the principle of superposition, and all of this field of electricity and magnetism is rooted in this principle.